So today is Priyanka ma'am told that we will discuss all these things and I'll try my best to give you best out of this. So you have to remember this every time, this table. And two other slides we have discussed in first session like qualitative data and quantitative data and then levels of measurements. These three or four slides are very important. And we know that here the dependent variable is quantitative in all conditions. And if today we will discuss about this Pearson correlation and Spearman correlation also. So here independent variable is quantitative and dependent variable is quantitative also. So we want to see some relationship. For example, height and weight. So how height affects the weight of the subject. We want to see BMI or weight and something else, but we have to know about the independent variable type, that is a quantitative, and dependent variable type also quantitative. Then we have to use Pearson correlation coefficient and Spearman rank correlation coefficient. And again, one group baseline, then 1 month follow-up, then 3 month follow-up, and then 6 months follow-up. That is a repeated measures or multiple follow-up only in one group or within group or single group. And the dependent variable is quantitative. For example, we are measuring BP, systolic BP at baseline, after treatment at 1 month, 3 month, and 6 months. And we want to like compare the mean BP at baseline, 1 month, 3 month, and 6 months. Then we have to use this repeated measures ANOVA if our systolic BP is normally distributed. Otherwise, we have to use a Friedman test. But what happened if our dependent variable is not quantitative? It means our dependent variable is qualitative or categorical variable. For example, death or alive. For example, hypertension, yes or no. That is nominal or ordinal in nature. For example, disease, minor, moderate, severe. So if our dependent variable is not quantitative and that is in qualitative nature or categorical nature, then what we have to do? Which test we have to apply? Here, all the tests are when we have to apply when dependent variable is in a quantitative nature. But what happened if there is a qualitative nature? Then we have to use chi-square or Fisher-exact test to find out any significant association between dependent variable and independent variable. So you have to remember that triple C, independent variable categorical, dependent variable categorical. So we have to use chi-square test. Categorical, chi-square. So there are some other conditions, and today we will discuss about all these things. So I have already discussed about this, that 2, 3, or 4 independent groups, qualitative or quantitative in nature. And dependent variable, as I told you, that qualitative or categorical, for example, hypertension, yes, no, male, female, alive, death, disease, present or absent. Disease symptoms, mild, moderate, and severe, or maybe 3 or 4 and more categories of dependent variable, okay, but in a qualitative or categorical nature. So we have to use chi-square test or Fisher-exact test. Where we have to use chi-square test or where we have to use Fisher-exact test, we will discuss. Now suppose in same group or in one group or within group, before and after in nature, for example, before treatment, we checked like pain, yes or no format, yes or no, pain yes, pain no. And after treatment, again, same patient, same group, we assess pain yes and no format. It means baseline to follow up and single follow up. You have to remember single follow up. So binary outcome, it's a binary outcome or condition like pain yes and no. Any condition yes and no, or present, disease present or absent, condition present or absent. So we have to use McNemar test. For example, at baseline, out of 50, 40 patients have pain. And after treatment, out of 50, 20 patients have pain. So at the baseline, 40 patients have pain, and at like follow up, 20 patients have pain. So is there any significant change? So we have to like find out the significant change. So we have to use McNemar test. And again, this is a McNemar-Bowker test. And we can use in the same condition. Independent variable is the same condition before and after baseline to follow up and single follow up. But you have to remember that here the condition is not binary. It's a condition here like disease symptoms mild, moderate, and severe, or more than two any category. So if there is more than two category before treatment and after treatment, then we have to use McNemar and Bowker test. It's like automatically will come in software, SPSS software. Now we have already discussed about two things. So next. So first of all, what is a correlation coefficient R or rho? We know very well about this. To find out relation between two quantitative variable, in which one is a dependent variable, for example, weight, and other one is independent, for example, height. So weight is depend on height. And you can see here in correlation coefficient, we have to make a scatter plot. Here in x-axis, there is a independent variable, and in y-axis there is a dependent variable, and we see there is a relationship. If height is increasing, weight is increasing or not, and how much weight is increasing. Or if, for example, if anything like independent variable is increasing, so dependent variable is decreasing or increasing. If decreasing, if one thing is increasing and second thing is decreasing, it means it's called negative correlation. If both things are increasing, it's called positive correlation. For example, if height increasing, weight increasing, so positive correlation. And negative correlation, for example, supply decreasing, demand increasing. So this is a negative type of correlation. Here on y-axis dependent variable, in on x-axis independent variable. This is a x-axis and this is a y-axis, and you can see there is a relationship. It's called perfect positive, perfect positive. One thing increasing, second thing increasing. So perfect, and this is a perfect relation. You can say single line. Now it's a strong positive correlation, but not a perfect correlation. It's a weak positive correlation. You can see there is a scattered in the observations, and there is no linear correlation. You have to remember there is no linear correlation. Maybe other type of correlation here, but no linear correlation. And you can see here this is a weak negative correlation. One thing is increasing, second thing is decreasing. This is a strong negative correlation, and this is a perfect negative correlation. And we can see that the value of R or rho is, this is a R or rho, value is R is from -1 to +1. You can say this is -1 to +1, equal to greater than -1 to equal to less than +1. So this is a value of R. Minus means negative correlation, plus means positive correlation. If we get R is equal to 1, it's a perfect correlation. If we are getting R is around 0.5, so it's around moderate correlation. So how much like R is defines as it's a direction and also it's a strength. If correlation coefficient is suppose minus 1.12, kindly interpret it. So we have already discussed that. See, R is the range of the R is from -1 to +1. So it's a minus 1.12. So it's a wrong, wrong calculation of R. So this is the interpretation of this. So we have to remember R is -1 to +1 always. Not below to -1 and not more than +1. And these are the table you can see here. R value plus 0.7 or higher, it's a very strong positive correlation. And you can refer this table and you can see his 0, 0 means no linear relationship. You have to mention there is no linear relationship. These are the, again, in negative. So it's a negative correlation, no negligible to strong correlation. Now R square or coefficient of determinant. R square. Here R, and if we square it, it's called R square or coefficient of determinant. So R square is a measure of how well a regression model fits the data. We will discuss in SPSS, no problem. It represents the percentage of variation in one variable that other variable explained, means a dependent variable and independent variable. For a pair of variable, for example, height or weight, R squared is simply the square of the Pearson correlation coefficient. So for example, squaring the height weight correlation coefficient, suppose height weight correlation coefficient is R is equal to 0.694. So we have to get R square, we have to square this, then we will get 0.482. And what's the meaning of this 0.482? 48.2%. Means, in other words, height explain this is an independent variable, explain about around half the variability of the dependent variable, that is a weight in a subject. So it's like, for example, it's around 30. So you can say 1/3 the variability of weight in a subject. It means weight is like 30% defined by this height, 70% by other variables, but 30% defined by this height, determined by this height variable. Now, simple linear regression. To predict the change in quantitative dependent variable, for example, weight, by change or manipulation in quantitative independent variable, for example, height. So if we change in height and we want to see change in weight, so we can like predict, we want to predict, so we have to use a simple linear regression. It is extension of Pearson correlation coefficient, and it is applied, and we have to apply it for understand relationship between a variable, negative, positive, strong, evaluate trends, negative, positive, weak, and make forecast. The main thing is make forecast or prediction about dependent variable due to independent variable. And this is, you have to remember this, minimizing the sum of squared error. In next slide, we will discuss about sum of squared error, can be understood as finding the best fitting straight line through the example points, through the observations. The best fitting line is called the regression line. You will see here, this is a regression line. On x-axis, there is an explanatory variable or independent variable like height. On y-axis, there is a response variable, or you can say weight dependent variable. And these are the observation. Okay. One patient here, height is here and weight is here. And you can see it, second patient, height is this much and weight is this much. So this is the distribution of the observation according to height and weight of the subjects. And this is a sum squared of error. You can see here is minimized if we use this line. This is error, you can see here, this is observed and this is best fit line, and you can see this is a difference, and this difference called error. When we square this error and we add all these error, these lines, when we like add all these errors, and this line from, you can see here all the error, when we like sum all the error, squared error, so it is minimized, minimum. Otherwise it is not best fit line. And when we talk about the slope, so you can see here, this is a slope, this is a delta y, there is a point here, so this here y1, and this is y2. So y1 minus y2, that is a delta y. Here x, x2, and here x1. So x2 minus x1, that is a delta x. So when we calculate slope, that is a delta y divided by delta x. So there is some constant value will come. So it's called a slope. And what about intercept here? You can see here where this regression line cut the cross the y-axis. At when we take x-axis at 0, x is equal to 0. Here x is equal to 0, and on x-axis, like x is equal to 0, this regression line cut the y-axis, and where it cut the cuts the y-axis, it's called a intercept. So it is also constant value. It's a w0, and it's a slope is a w1. And when we talk about this regression equation or regression line, so it's a y is equal to dependent variable, so y is equal to w0. W0 means this is intercept, plus w1x. W1 is a slope, and x is a explanatory variable. For example, here height, and here weight, and these two are constant. So how we do it? We can see. So this is a, in other another terms, y is equal to a plus bx. It's very simple. Y is equal to a plus bx. Okay. So where y is a dependent variable, for example weight, and x is an independent variable, for example height, and a is the intercept where x is equal to 0, at which what point regression line cross the y line, and it is maybe above this in positive, and this is negative for y, so it may be positive and it may be negative. We have to see. And b slope we have already discussed. Now let's have fun with SPSS. Same thing we have already discussed. I have just changed here in methodology. Randomly selected 120 patients, 60 in each group, did 3 months follow-up and 6 months follow-up. Earlier in previous class, we have did only 3 month follow-up, but now we have 3 month or 6 months follow-up, because I have to use a repeated measure ANOVA. If only there is a 2 follow-up, baseline and 3 month, baseline and 3 month, then we have to use Patty test if data is normally distributed. Otherwise Wilcoxon signed rank test. But for repeated measure ANOVA, follow-up must be like 3 times we have to take readings, baseline, 3 months or 6 months. Follow-up, it like 2 follow-ups can go, but baseline 3 readings, repeated measure 3 readings, baseline, 3 month follow-up and 6 months follow-up, and maybe 12-year follow-up it goes. Okay. So we want to see, is there any significant improvement in the survival of patients at 3 months due to treatment? So survival means patient death or patient alive. So it is a dependent variable is in qualitative nature. And we have 2 category, 2 group, control group and treatment group. So control group, treatment group is a categorical variable, and survival is a alive and death also categorical variable. So here category C, here category C, use third C, that is a chi-square test. Okay, so we will use for this. Is there any significant correlation between height and weight? Oh, it's very good. If normal distribution, we will use Pearson correlation. Otherwise, we have to go for Spearman rank correlation coefficient. And other and we can change this question: how does height of the subject affect their weight? Same thing. Effect of patient's age on the 3-month quality of life score. Also, patient age is quantitative. 3-month quality of life is also quantitative. So we can use Pearson Pearson correlation coefficient or Spearman rank correlation coefficient on the basis of normalcy. Is there any significant change in WHO quality total score from baseline to 3 months to 6 months? It means we have taken 3 times reading repeatedly: baseline, 3 months, and 6 months. Follow up within groups. So we have to use repeated measure ANOVA if quality of life normally distributed, otherwise fried mean. Okay. To assess the effect of treatment on vision or functional vision status at 3-month follow-up. So effect of treatment, it means we have control and treatment, it's categorical. And vision and functional vision status, it means there is a problem or there is no problem, it means yes and no, also categorical. So here category, yeah, here C and here C, then we have to use our third C, that is a chi-square test. Is there any significant change? If there is, please see this last line, last 2 sentences. Is there any significant change in vision or functional vision status from baseline to 3-month follow-up within each group? Treatment separate and control separate. So at baseline, there is a vision problem, yes and no, or functional vision problem, yes and no. And at 3 months after treatment, we want to see how many patients have vision problem. There is an improvement or not. So we have to use here McNemar or Bowker test. Now, so I want to see this slide before proceed for SPSS. This is a chi-square. You will be familiar with when we use by SPSS. This is a cross step. This is a chi-square. And we did this itching. Itching is 0 and 1. This is a nominal category. Itching yes or itching no. Itching no, itching yes. Okay. And this is a gender. Gender 1 and 2. Okay. So 1 is like male or female. And we see if there is any association between according to male and female, if female has more itching or not, we have to see. So whenever we do this cross tab or chi-square test, please see this table, and after that you see, okay, 12 in male, 48 in female. Okay, my data is all right. Total 60 patients, very good. Okay, and then you have to see this first chi-square test table. You have to see this here, A, below this A. One cell 25% have expected count less than 5. The minimum expect count is 4.60. We will discuss about this. What is it? So please remember this. It is very important. Please remember. If here 0 cell account, you remember this only. If here 0 cell, then we have to use Pearson chi-square test p value here, asymptotic significance 0.017. This is chi-square value. This is a degree of freedom. Okay, and how we got this degree of freedom? We got degree of freedom here, rho minus 1 multiplied by column minus 1 for chi-square test. Okay, rho minus 1 multiplied by column minus 1. Number of row minus 1 multiplied by number of column minus 1. So how many row here? Here 2 row. one for no itching and one for yes itching. There are two row. And how many columns? You can see for gender there are two column. So 2 minus 1 multiply by 2 minus 1, that is a 1 multiply by 1, that is a 1. So it's the degree of freedom we get here 1. So if you will see here in A below this table, A one cell. So if here 0 cell, you will see here 0 cell, then you have to use this Pearson chi-square p-value asymptotic significant two-sided 0.017. It's a significant. There is an association of gender and itching. Okay, there is a significant association of gender and itching due to any reason. And if you see like here 1, 2, 3, 4, 5, whatever cells you see here, then you have to use this Fisher exact test p-value, and this is a exact significant two-sided. This is a 0.020. You can see both are significant here, so no problem. But sometimes you can get this chi-square p-value significant, but you will not get this Fisher exact test p-value, and you will provide this result. It means you are conducting type 1 error, because type 1 error is a rejecting null hypothesis when it's true, and null hypothesis is there is no association between itching and gender. There is no association between itching and gender. But if you are taking this p-value, Pearson chi-square p-value, you will reject. Suppose this is significant, this is not significant, and you will not see here. And taking this p-value, and you are presenting your result. So you are conducting type 1 errors, more serious errors. And your paper may be rejected from journals because they demand your data, and then they analyze, and then they say, okay, your paper is like your analysis is not good. You provide wrong results. Okay, so you have to see all these things. So now we start our session with SPSS. Have fun with SPSS. And this is my data sheet. I think, I hope you have entered your data sheet in SPSS, and I want to enter here. So it's a shortcut method. I always prefer shortcut method because I don't much time here. Just click it and then drag and relax. Oh, this window will come, okay, automatically. Very good. Okay, only one. Yes. There is a two sheets you can see, but I know data in only one sheet. So I have to click here. I have to check these three check box here. Okay, okay, very good. And then I have to click OK. That's a very simple you have done, I think. This is output window. And this is my data sheet. Again, I have to do treatment and control. I have to give coding, and then I have one variable that is a outcome variable, or I want to say 1 minute. I want to see here. I have taken pic of that PPT. Survival, okay? So death and alive. I have outcome variable. So this is a treatment group or control group. I have to give this code. So just click here on age, then right click, and then insert variable. You know very well about this, you know. And then I want to give one code, one number, one, then click here, again click here, control C, then okay, up to this. Very good. Down and right, down, shift and down arrow, then control V. I will not explain about this again, then click to, then again click to, control and C, then shift and down arrow. Okay, I have given this, very good. Then control V. I want to give this like name and decode. I want to decode. So I have to click, double click here. I got it. Okay, group code. And then value, I want to give one for treatment. So treat, two, control. Okay, very good. And click on add value label. I think you are familiar with this. You have to click a, you can click add. So, and you have to click this OK button. This is value label and then OK button. Then you have to click on data view here on like below this left side data view. And I have to see where is my survival or like live or death. So I like scroll this from left to right, and what I see, okay, here I have, this is my data here. Okay, I have taken, I think, wrong. Oh, very good. I have taken 3-month follow-up. I have taken wrong Excel sheet, no problem. Then again, I have to click here, open new data for, and then I have to click this SPSS statistics, then Excel, because this is in Excel. I know that where is my Excel sheet? Here my Excel sheet data 29, okay. Then open. Why it's come according to this? 1 minute. There is some problem, I think. Oh, this is 29. I have to see. Yeah, this one data sheet 29. This one. Sorry, I have to take this data sheet. So there is, I face some problem. Okay, but I have checked this. So I have to start again. No problem. There is some problem in opening data sheet. I have choose another data sheet. Sometimes it happens. But when I see there is no 6 months follow-up, I have to wait. Sorry for interruption. And this is a like best way. You have to click this button here, restore down. You have to click right side up. So this is minimize. Then you have to drag it. You have to make 2 window here. And want to like import this, click here, right click on pad and then drag this and leave this. Okay, then I have to see what is problem. I think there is some problem in, I have to see this is final data ANOVA 20 and this is 29. Okay, then I have to click OK. I have to see data have entered or not. Okay, data I have entered. Okay, right sheet I have entered. No problem. So already you can see here already I have given group code. So I got some confused that I have already given this group code. So why I have to give? This is a group code and I want to decode it. So just double click here on group code and then please go in value label, click here on none in front of none and then value 1 for, you have to give in value label, this dialog box value label, then click on value and label treat, okay, treat and treatment. Click on add button. Okay, this come here in this box and then 2, I have given 1 and 2, then control. Then okay, click add and then click OK. Here, then I have given. Now I'm going to demo on chi-square and Fisher exact test because I want to like find out any association of group or effect of treatment on survival at 3 months. So you have to click this analyze button, then descriptive statistics, and then cross tab. click this cross tab here, and you see here, you want to see according to this effect of treatment. So you have to like click on group, and then this group will come in column. So please click on here, this arrow. So this group will has come here, and then where is your, you have to like uh, scroll down, and where is your alive and death. So this is alive and death. You can see here, this is alive and death, alive and death at 3 months, or outcome code. I have given outcome code also. Okay. And this is alive and death. So I want to take this alive and death 3 month. You have to click here, and then this is arrow in row. We have to put it in row. This will come here. Then you have to click, this is here, you can see right side, there is a exact. So please don't forget, never forget to click this exact, and this dialog box come exact test. There is a asymptomatic, Monte Carlo, confidence level, and then this is a exact. You have to click, every time you have to click exact, and then click continue. Okay. Now statistics, you have to go in statistics, click here, then there is a chi-square test. Very good. Then click here. Okay. And then click on continue. No need to like select other things. You have to just click continue. You can see there is a McNamara test. So when we use, we will like discuss about this. Okay. We have to click here, click continue. Then this is a cells. You have to click on cell button. And you have to, like, this is a percentage, this is a count button, count is observed, this is expected, here expected count less than 5. So this is the expected count. If you want to see, so we have to click here, otherwise leave it. And there is a percentage, and percentage row, column, and total. So generally we want column percentage. Sometimes we can use, otherwise you can leave all these things. You have to just click column. So you will get percentage also. Then click continue. Then click OK. So what you see here, there is a, you see here, okay, 120 patients, 16 each group, treatment, date at 3 months follow-up, out of 60, only 4, and this much percentage, 6.7. And this is a 60 out of 60 in control, 19 expired, 31.7% expired. And this is a survival, alive survival. So survival is high in treatment group compared to this in control group. It is significant or not, we have to see this. Before we have to see this, we have to see this A is 0 cells. We have to see this chi-square test table. 0 cells, oh, 0 cells. So I have to use Pearson chi-square value, degree of freedom, and degree of freedom. How we will get degree of freedom? I have explained you, and this is a like a symptomatic significance two-sided. It's a highly significant. So survival rate is high in treatment group compared to control group, or death is significantly high in control group compared to treatment group at 3-month follow-up with this p-value. Oh, I'm very happy. So treatment is successful. Very good. So I'll publish my data, and after some time in newspaper with my photo, I will like get news, big news. Okay, so this is like beauty of statistics. All depends on this SPSS or any other software. This is a chi-square and Fisher exact test. Okay, suppose we get here 0, so we use this one. Otherwise, if we get 1, 2, 3, 4, so we have to use this Fisher exact test p-value, exact significant, two-sided, almost same. Oh, equally same. Very good. Okay, it's very good. So we have to use this. But what happened? I want to see, like, I want to show one thing, that is, so I have, yeah, this one. You see, and what I told you that this is anxiety and area posting. Anxiety, yes and no. There is a chi-square test or Fisher exact test which we have to use, and why. And this is a cross tab. So this is a like categorical variable. This is ICU and ward is also categorical variable, area posting. Okay. You see here, you want to see there is a significant association of anxiety and working in ICU or ward. So I have to apply this chi-square. or Fisher exact test. But which p-value I have to use? Please see this here. A, you see this. One cell have expected count less than 5. If suppose if I ignore this and I took this Pearson chi-square p-value as asymptotic significant, oh, very good, it's come significant, I'm very happy. And what happy in ward who are working in ward is have high anxiety level compared to ICU. And what happened? Okay, maybe there are, I have to like discuss all my findings, maybe due to this, due to this, due to this, and then. And when the more intelligent statistician see this, or like reviewer see this, oh, this is one cell. So he had to take which p-value? Fisher exact test p-value. And what is p-value? This p-value. And this is non-significant. If there is no association of anxiety in ICU and ward, so I committed a type 1 error. I reject the null hypothesis when it's true. I committed type 1 error. You know, error is like very dangerous. So this is a Fisher exact test and this, okay? Now I proceed for Pearson correlation coefficient. Find out weight and height and weight. It's very simple, no problem. You have to click, come on platform, SPSS platform. Where is my height? Oh, where is my height? My height is here. You can see height in variable, you height in meter, height in centimeter, and height in kilogram. And what I see, there are a lot of decimals here. I don't want these decimal. I want to remove. And how I remove? It's very simple. Just double click here, shortcut method. Double click here, then there are decimals, 15 decimal. Why came here? I don't know. So I need only like one decimal. And also BMI 15 decimal. I just correct along with this. And then again, I have to click this height mate in front of height mate 11 number. So I came here. Okay, I got it. But I need two decimals. Okay, you know that height in like 1.5 to 1.50 something. So I think I should do some favor with decimal. So I took two decimal. Oh, very good. And where is my weight here? So which is dependent or which is independent? Height is independent. Weight is dependent. So I want to, like, which test I have to apply? Quantitative variable, I have to go Pearson chi-square if both are normally distributed. Otherwise, Spearman rank. Suppose first time it's normally distribute. Second time we will say, okay, it's not normally distribute. So want to like check this correlation. There is a correlation or not. So I have to click analyze here. And then where is the correlation? Oh, here is a correlate, very good. So, and then you have to click bivariate, very good. This will bivariate correlation window come. You can see there are variable, okay, we have to study, and these are the variable we have to find out correlation. This is options. We don't need all these things, okay. And there are correlation coefficient. You can see here, Pearson and Spearman. I want both. It's very good, okay. Along, okay, together I can get it to Pearson or Spearman. And where is height and weight? So please click on height and click this button, weight, like height, sorry, weight, and click this button, weight come here. Then, okay, there is any difference between if I like find out correlation with the height and weight, height in centimeter and height in meter, there will be difference in correlation. Okay, check here. So I have to click height centimeter, and then this arrow, I have to click here, and again, height meter. I want to see, okay, there is some difference or same correlation, because this is a mathematical calculation. I think it must be same, okay? Okay, all variable I want to like correlate, like come here, and then I have to click okay. Okay, I got my results. Okay, very good. So what I see, this is a correlation. And which type of correlation? This is a Pearson correlation. You can see here. This is R value, and this is a significant two-tailed. This is a P value, and this is a N. N is, I know that 120. Okay, 120. There is no missing. Very good. And this is a non-parametric correlation. You can see here. This is a non-parametric correlation. Spearman row correlation. Okay, and then also correlation value, row value here, and this is a height and weight correlation. Please interpret first table correlation, Pearson correlation. This is weight and this is height. Weight and weight correlation one, always one. I know that it's always one, perfect correlation. No need to give p value here. And height in kg and weight in weight in kg and height in centimeter r is equal to 0.496. It's a moderate positive correlation. There is no negative here, positive correlation, and p value is 0.000. If you double click this, and if you want one more decimal, just click here, you will get this type. Oh, it's a very highly significant. It's a highly significant. Okay, 0.0000, something like that. So it's highly significant. I want to see that weight kg and height meter same, because it's a mathematical calculation. So same correlation value you will find. It's also significant. It means height and weight is highly significant correlated in our sample. And I think it must be, otherwise maybe there is a big problem. If you provide data like this, that there is no correlation in height and weight, there is a question mark. How come it's possible? Must be there is a correlation. Okay, then see this Spearman-Rowe correlation coefficient. So weight kg and height centimeter, it's a 0.482, and where it is a 0.96. So if our data is normally distributed, we have to use this. Otherwise, we have to use this, and this is also moderate correlation. Little bit less, but also moderate correlation, significant correlation, positive correlation. Height in increasing, weight is increasing. Very good. Okay, so I can write down my results. I check normalcy, not normal distribute. I have to use this non-parametric test, Spearman-Rowe, and this p-value, this, and Rowe value 0.482. And my result is this, n is equal to 120. I have to provide. So there is a significant relationship. Okay, so this is about Pearson and Spearman rank correlation coefficient. And I want this scatter plot. So how I want scatter plot between height and weight? I have to click this graph button here. You can see file, edit, view, transform, insert, and this is a graph button. I have to click. I want scatter plot. Click here. Then go in legacy dialog box, and there this is scatter plot. You can see here this is a scatter plot. Just click on this. I want simple scatter plot. There are multiple other things. I don't need this. I want only simple. Click here and then define. Click on define. You will get this, and what I have to enter in y-axis and what I have to enter in x-axis, you know very well about this. And if still you don't know, it means there is a problem in, I think. So I have to click weight, and I have to click weight in y-axis, and then I have to go whatever I can take. Height in centimeter or height in meter, I can take, no problem. So I can take height in centimeter, no, because same graph will come, x-axis, and just click OK. It's very simple. You will get this graph. This is a moderate correlation, height centimeter and height in, you can see height in centimeter here, 150, 160, 170, 180, and some are more than 180. And this is weight 20, 40, 60 kg, 80, 100, and 120, below 120. Okay, so these are the. And if I want to add like reference line here, then I have to double click it. You see this double click to activate. So I have to double click it. And this chart editor window will come. And why I have to add? I have to reference line automatically. Okay, so I have to click this is a reference line button. You can see here this is a pistol button. I like tell it that is a say it's a pistol button, very useful button. I will show. So this is a like a reference line button. You have to just click simple it, and you will get this line. And you can get this R square here also. Oh, okay. 0.246. Otherwise, you can square this R value. So 0.246. It means 24.6% weight is determined by height. And rest percentage, determined by other variables, which we did not include in this model. And if you want to like remove this, this is not looking good. If you want to remove this, this is a equation line. This is a best fit line. Minimize like sum of squared, you know, sum of squared of error. This is best fit line. And this is intercept here. This is intercept in on x is equal to 0. This line cuts here around 44, 42 something. This is a y is equal to 42. So here we have to see. So this is the best fit line. Okay. So we want to remove it. This is like property button. You can say attach label to line. I don't want attach label. So click just here and then apply. If I want to like change color here, first apply, then what we see, this automatically go on this label. I want to change this like red line. It's coming significant. I want to highlight this. This is a line option in property. You can see, click here. And this is a line color. You can add line color. I want to add red. I want to like increase weight. Okay. So this is around 2. I want to like width of the like line. I want to increase and then apply. Click apply. Click here, red will come. And then on weight 2, I have to select 2 point and then apply. You can see, okay, very good. It's a very good result. I can save all these results. This is a scatter plot, very beautiful plot I got. I think I'm very happy with this. Now this like Fisher exact test, chi-square, and then we go for simple linear regression now. R square scatter plot we have done. Simple linear regression. So what is simple linear regression? In height and weight, because in simple linear regression, dependent variable is a quantitative. Independent variable may be like you can see qualitative in nature, nominal or ordinal in nature, but or in a, like a quantitative nature. But dependent variable must be quantitative in nature in a simple linear regression. So how we apply? You have to click analyze button. Then there is a regression. Okay. Click on this button, regression, and there is a linear. You have to click linear. Okay. Then you will get this linear regression. And this is a linear regression is extent of correlation coefficient, mainly Pearson correlation coefficient. Okay. Remember this. And in dependent variable, what I have to enter, you know, I have to click weight and then I have to enter weight here. Simple. And in independent variable, what I want to add, height in centimeter. I want to add height in centimeter. Click here. Very good. So both I have entered in dependent and independent variable. Please don't make mistakes. Height in dependent and weight in independent. Please don't make mistake. So you have to remember which is dependent and which is independent variable. Then there are some other like statistics option. You just click. This is a regression statistics. Estimate beta coefficient. This is a regression coefficient we called, and this is I want 95% confidence interval of this beta coefficient. If you want to change, you can change here. Just type here 99, but generally we want 95, and then click OK. We don't want any other things. There is no need of this. Click OK. Then option. Okay, there is no problem. We have to like according to default we proceed. Then click OK button. So you have to click statistics and confidence interval, then click continue. And this is enter method. We prefer enter method for this because it's a simple linear regression. So there is no need to like change this method. And then click OK. So what we get, we have to see enter method. We have, and this is a dependent variable. This is a regression variable entered or removed because we have entered only one variable. And enter method, and when we use stepwise backward, there is a remove variable also over there. Dependent variable is weight, okay, and then independent variable is predictor is a height, and you can see this is a r square value, and this is r value, and this is a r square. We got in also in a scatter plot, and this is a adjusted r square. So you can see they only just a little bit, though both are similar something. Okay, so and we have to see this is a model fit. ANOVA test, this is a model fit. So it's a fit because we have to see this significant p value. If it's significant, it means our model is fit. Means height significantly depend, like weight significantly depend on height. Our model is fit. If we get this p value below, like more than 0.05, so this model will not fit. So very good, we get this ANOVA, and this my model is fit, and this is a coefficient. We have to see this table, and we have to interpret this table. You have to see. And as I told you that there is some mistake because this is a dummy data. Okay, and I got here beta coefficient. What is it? It is a like a beta coefficient, and beta coefficient, and this is beta coefficient of constant minus 86.240. This is an unstandardized coefficient. We have to take a unstandardized coefficient, and this is for constant, and this is for height. And this, and we have to see this is significant p value. So constant is also significant, and height centimeter is coming also significant. It means weight is significantly depend on height. So we have to make a equation from this table. So how we make equation? We have to use for, I want to see how to make equation using this model. So I think you, after that you can make this equation. I want to show on, this is our, I want to show equation. Okay, write down here. So y is equal to, regression equation is y is equal to a plus bx. So y is height, weight. So weight in kg is equal to a. A is your constant. So what is constant here? Minus 86.24. Okay, minus 86.24, and then plus, this one is a plus sign, then you have to click here, this is plus, shift and plus, and then what is b? B is your slope, and what is slope? This is the slope of height, because slope is something, okay, not like alone, it come with like roof slope and something floor slope. So the slope is along with something. Okay, so you have to write down here, this is 0.901 and multiply by height in centimeter. Okay, you have to remember that height in a centimeter. So what do you meaning of this? What do you meaning of this? So if we increase height, mean height, we have mean height in our data, mean height. If we increase in our sample, given sample, if we increase 1 unit of height, means 1 centimeter, if we increase, so how much weight of increasing, or the patient, weight of the patient? So just click here, I want to get, first of all click analyze descriptive and then frequency. Then I want to see height centimeter, click here, mean of this height centimeter. This is a quantitative, so please declick it. And then in statistics, we have to go mean. Just I want to see mean. Okay, click continue. And then I want to see just mean. So what is mean? Mean is 164.7. So if I increase 1 unit from mean of the height in my population, sample population, so what will be like weight change. You can see here. So I have to put here equation weight is equal to minus 86.24 plus 0.901. 901 means equal to 1, you can see, and multiply by 164.70. Then if I take it as a 1, because calculation will be easy. So what will be weight? So weight will be, you can see here, 164.70 minus 86.24. So you have to calculate weight. What is the weight? If I increase from 1 unit, so what will be weight? Around 80, around 82 or something like that. Okay, 80 kg. 80 kg weight. I got 80 kg weight. This is a regression. We can predict for using this regression. And whatever we weight height, we put it here. This is a simple, this is a average. Okay, this is for average. We can put height in centimeter, whatever we want. Okay, suppose one patient has height around you can say 164, 150. So what will be weight? We can check it. Weight is equal to minus 86.24 plus, you can see, and it's equal to 1. Okay, suppose it's equal to 10 and 150 centimeter. What will be weight of this patient? I want to check. So it's around, you can see here, okay, like around 70 kg, suppose. It's just around 70 kg. Oh, very good. It's a like usage of regression equation. But with weight, with correlation coefficient, we will not get. But using this regression, simple regression, we can predict. Okay, we can predict. So regression is for a prediction. Okay, thank you. Then we have to move next. Next is a repeated measure ANOVA and then predicament test. So suppose I want to see within group comparison of the baseline 3 months and 6 months, like follow-up, mean comparison of quality of life from baseline to 6 months within group. There are three measures. We have taken three measures. We have taken three measurements: baseline, 3 months, and 6 months. So in three measurements, we cannot use PAT test. So we have to use repeated measure ANOVA. More than two, we have to use more. If there are more than two measurements, we have to take a repeated measure ANOVA. If data are normally distributed, otherwise we have to go for fragment test. So it's very simple. But within test, I told you that we have to separate, we have to split file. Within group, always we have to PAT test, we splitted file. Again, repeated measure ANOVA within group, we have to split file. And when we use McNemar test, this is also a within group. So we have to again split the file. So I'll tell you all the test after. Just click here data, and then this is a split file button. Click here. What happened? Oh, very good. And then you have to click on this split file button, like window will come. You have to organize output by group. You have to click here. And then according to group, you have to split file. So click on group code and then this arrow, group based on, this will come here, then click OK. So you have to click OK. Oh, I have a splitted file, very good. Now, repeated measure ANOVA. Where is repeated measure ANOVA? I know that I have to use repeated measure ANOVA. Where is repeated measure ANOVA? It's a very simple, no problem. Analyze. Then this is a GLM model. It's called a GLM model, high-fi statistics. Now, and tomorrow you will face on more high-fi statistics. And next day after tomorrow, more and more. So from today, like from now, you have to face high-fi statistics. This is called GLM model. Then you have to click repeated measures. Wow, very good. Repeated measure. Click here. And you will get this repeated measures define factor. Okay. So factor, I know that this is quality of life. So you have to QOL, QOL, and level of measurement. This is a dependent variable. Level of measurement, baseline, 3 month and 6 month, 3 times. Level of measurement, three times I have taken. Then click add. It's come here. Quality of life, 3. Very good. If there is a 4 measurement, I have to like put here 4. Then define. There is no need to measure name. Just define here. Click on define. Now this repeated measure dialog box will come. This 1, 2 and 3, this is within subject variable as I told you. And 1, 2, 3, what you will put here? I think you have got this. What I have put here? This is a total quality of life baseline. You have to put in 1. Click this button. Then 3 month. Where is 3 month? This is 3 month. Very good. Put it here. And then 6 months. Oh, very good. I got it. 6 months. And then this. Very good. I got it. Then plot. Please click on plot. This is a time series plot. Please click on plot. I want quality of life plot. I want horizontal axis. You have to click here and then click on add. This is a quality of life. This is a repeated measure plot, profile plot. Here factor, quality of life. I have to click on this, and then horizontal axis, I want this. So I have to click quality of life. I want a line diagram for this. Okay. Then I have to click plot add button. Then it's come, and I want line chart. Okay. I want line chart here. Then click continue. You can like take a bar chart and with including like a error bar. Okay. So click continue. Oh, very good. Then don't what happened? Oh, click here. This is estimated margin means you have to click quality of life, and then you have to click and then display means for, and then again you have to click compare main effect, and what you get LST. You click here, and this is our Bonferroni favorite test, and Bonferroni for post hoc comparison. Why post hoc comparison? Because there are 3 measurements, and repeated measure ANOVA null hypothesis is there is no significant mean difference between like baseline to 3 month. There is no significant. They are both are equal, and like baseline to 6 months and 3 month to 6 months. This is a null hypothesis for repeated measure ANOVA. What is alternate hypothesis? At least there is a one significant, only one pair significant difference. Maybe baseline to 3 month, or maybe 3 month to 6 months, or maybe 3 month to 6 months, or maybe baseline to 6 months. So this will be done by Bonferroni correction. Bonferroni. We have to like correct it. So click continue. Then here option, you have to click option button. There is a descriptive statistics. Just click here. And no need, and we don't want anything else. Just click here. You have the significance level 95%. Yeah, it's a default. Very good. Continue. And then click OK. We have already splitted file. Very good. You can see it's a general linear model. This is a group for treatment. Very good. And you can see 1, 2, and 3. What is 1 and 2 and 3? 1 is total baseline, 2, 3 months, 3, 6 months. You have to remember this. And this is a treatment group. And this is baseline mean and SD, 3 month mean and SD, and the 6 months mean and SD. There are 57, maybe 3 like loss to follow up, something like that. Okay. We don't use this multivariate test effect, something like that. No need to using this. We have to use this mostly test of sphericity. And you have to remember If this p value come non-significant, if this p value mostly test of sphericity p value come non-significant, means greater than 0.05, then from within test of within subject effect, we have to take quality of life sphericity assumed p value. This is p value, this is degree, like ANOVA value, this is f value, that is ANOVA value, this is degree of freedom, okay, between group, and this is degree of freedom within group 1, 1, 2, and 2. There are three measurements. So 3 minus 1, that is a 2, and there are total how many? 57, 57, 57, and then 57, and you have to like calculate this degree of freedom according to this. Then this is like 57, 57, and minus like 57, you have to calculate according to this. And this is quality of life, this is p value, you have to see this is p value for repeated measure. This is a highly significant. It means eight list there are two means significant difference, maybe baseline to, maybe baseline to 3 month, and maybe baseline to 6 months, or maybe 3 months to 6 months. How we find out this? So we have to go below, and there is a pairwise comparison table. There is a Bonferroni correction adjustment for multiple comparison Bonferroni. Then you can see here what is 1, 2, and 3. 1 is baseline, 2 is a 3 month, 3 is a 6 months. You can see 1 and 2, there is a main difference is this much, and it is a significant p value. Yes, it's a significant, it's a Bonferroni corrected p value. Oh, very good, it's a significant. 1 and 3, baseline to 6 months, it's also coming significant. So we can conclude in treatment group, quality of life increasing from baseline significantly at 3 months and at 6 months. Okay, then we can see like baseline to 3 months and baseline to 6 months. When then we have to see here, this is 3 months, this is baseline. So here this is baseline to 3 months, it's coming significant. All okay, obviously this is like 3 months to like 3 months to baseline, it's also coming significant. Same thing. But you can see here 3 months to 6 months, there is a p value 1. It means quality of life in treatment group is not, it's the same in 3 months and like 6 months. There is no significant difference. So this is a conclusion of this. And you can see here, this again, same thing. This is for treatment group. You can see here, same thing for control. This is a plot chart. This is a plot chart. You can see here, this is a time series. This is a baseline. This is 3 months. This is 6 months. If you want to change it, you have to double click it and want to make this chart editor will open. You want to like give it baseline. So you have to click here, and this will, you can baseline, you can change it. Very good. Okay, and then again you can double click here at 2, this will highlight it, and then you can get 3 months, and you also you can click here and then 6 months. So it's a 3 month baseline, 3 months, 6 months. You can see baseline to 3 month increasing significantly, but not from 2 months, 3 months to 6 months. You can see here. And what this and if you want to add the like value of mean, you can use this, okay, gun. You have to click here, then this will come in your cursor, then click here. Okay, this one come 283, double click 313, and this double click, you have to double click here 314. So only just one difference here, significant difference. And if you want to remove this gun, you like you have to click again here. Okay, so this one come. Oh, very good. Click cross. I need this chart. Again, you can see here in control, same thing in control. You can see this is a Moseley test of sphericity. P-value is less than 0.05. Then you have to, okay, sorry, I forgot this. If this p-value greater than 0.05, then you have to use sphericity assumed p-value. If less than 0.05, then you have to use a greenhouse geyser correction. And this p-value, but both are similar. So in both case, in treatment and control, you have to use this p-value greenhouse geyser, not sphericity assumed, because sphericity assumed is violated by Moseley test of sphericity. Okay, then you have to use, this is coming significant, and which pair you can use here. Oh, in this 1 and 2 and 1 and 3 is all coming significant. How come possible? It's a control group. How come it's possible? So I will see graph. I see, oh, okay. In graph, 6 months quality of life is decreasing in control group, and decreasing control group is coming significant. It means my treatment is effective. Very good news for me. Good finding for me. You can see here, all are coming significant. Baseline to 3 months coming significant. Baseline to 6 months coming significant. But you see, 2 months to 3 months coming significant. I got shocked. Okay, in treatment group, it's not coming significant. But here it's coming significant. But I was very happy that when I see it, oh, it's decreasing. So this is like a repeated measure. You can like activate this, you can change this color, whatever you want to do. If I want to like write down here, this is estimated marginal mean, I have to double click it, and then I have to double click, and then I can write down mean quality of life score. Mean quality of life score. Okay, mean quality of life score. Then you can just double click and play with this. No need to like worry. Okay, then I can save these documents here. Now I want to show you two tests. I think I will take only 5 or 10 minutes more, nothing more than this. I want to like, if the quality of life is not normally distributed, then what I have to do? I have to, there is a repeated measures within group, then I have to use Friedman test. And where is Friedman test? Non-parametric. So just click OK on analyze, click non-parametric test. Then there is legacy dialogues, and here is a care related sample. There are two related samples. This is a Wilcoxon. I want care related samples. So click here, care related samples. Okay. Then this is test variable. No need to worry. This is already Friedman is applied here. Then you have to put your value here. Baseline, 3 months and 6 months. And just click OK. Very good. And I got result. In treatment group, it's significant. And please leave this rank. This is a Friedman test, real rank. I don't need rank. This is a test statistics of Friedman. This is a chi-square value, n and like degree of freedom. There is a 3 groups, so 3 like 3 times measurement, 3 minus 1, that is a 2. And this is a symptomatic, highly significant. Okay. You can see here also, this is also in control significant. So same thing. Okay. Same thing like null hypothesis, but here null hypothesis is not a median. You have to use a distribution of your data. You have to use here, because we use a median in table for these non-parametric test median, but null hypothesis, generally we are using median of one group is significantly different from second, but it's not right. So you have to distribution of data, dispersion of data. Main thing is dispersion of data we have to see in a non-parametric test, whatever like Mann-Whitney, Wilcoxon, and repeated measure like Wilcoxon and Friedman test. Distribution of data. So like there is no significant difference in the distribution of data in like baseline to 3 month and baseline to 6 months and 3 month to 6 months, because our this is a null hypothesis. And alternate hypothesis, eight list eight list baseline to 3 month or baseline to 6 months or 3 month to 6 line, eight list, there is a significant difference at 2 times when we compare in distribution. How we get it? In this, I have to double click it. This is okay. No need. Okay. So for post hoc analysis for Friedman test, I have to further analyze. And how I have to further analyze? I have to, because post hoc analysis I have to do for Friedman. So click analyze, then click non-parametric, and then click here. Don't go in legacy dialogues again. Related samples, please click here. This dialog will come. So just click, this is objective, non-parametric, 2 or more related samples. You just click field, and you know, in field test field, this is a field, this is a test field. And what I have to like bring here, I have to bring here 3 variable, baseline, then 3 month, then 6 months, then click, okay, all are here. Then click setting, here setting, you have to click settings, and then you have to use this customize test, click here, customize, and then there are a lot of tests. You have to use comparison distribution, compare distribution. Friedman two-way ANOVA by rank, all pairwise. You have to use all pairwise. This is a multiple comparison. Just click run. Okay, my work has been done. Very good. This is a treatment. This is a like p-value, rejected null hypothesis. Okay, this I have already seen this. This is a rejected. But what about multiple comparison? You can see this. This is a multiple comparison. This is unadjusted p-value, and this is a adjusted p-value. You can see this is a Bonferroni corrected p-value. This is from baseline to 3 month, unadjusted is this, and adjusted is this. So there is a baseline to 3 months significant, and baseline to 6 months also significant. But again, as repeated measure, 3 months to 6 months p-value is this. You cannot take this. You have to take this p-value with this test statistics and this p-value, corrected p-value. And no need to, and in again in this is a treatment group, so use this, and then again control group, ignore these, all these graphs वगैरह you have to ignore. This is hypothesis test, rejected null hypothesis for control group. Then you have to go, this is Friedman test p-value. You can see Friedman two-way analysis, and then you have to see this is multiple comparison, baseline to 6 months, baseline to 3 months, but not 6 months to 3 months. There is no difference. So it means they comparable, but in repeated measure ANOVA significantly decrease, but here not decrease. But if data is not normally distributed, you have to follow this. Otherwise, you have to take that a repeated measure ANOVA. You have to write down in your finding. Then how to calculate median and IQR? Just split. We have already split. Just go in analyze, then descriptive. Oh, 1 minute. Analyze, click analyze, then descriptive and frequency. And I want, please bring this back to height. I want median and IQR for all. So click like for this baseline. Then 3 month, very good. 3 month, where is 3 month? This is 3 month, and this is 6 month. And then click statistics, and this is median and IQR. No need to mean. I can use minimum and maximum also in dispersion, minimum and maximum. I think you are familiar with this dialog box. Continue, and then okay. These are the median and IQR values you can use for your results. Median and IQR, minimum, maximum, median and IQR. This is median, this is also median. 50, this is IQR, 25 to 75. You have to write down 244.0 bracket Then IQR 206.0 to 273.75 for baseline in treatment group. This is a 3 months in treatment group. This is a 6 months in treatment group, and that is a p value is 0.001. And then you have to write like Bonferroni correction. You have to write down Bonferroni correction. You have to write down that corrected p value. Okay, group 1 like baseline versus this p value, baseline versus 3 month, this p value, 3 month versus like 6 month, this p value. You have to all the data in your in a table. So this is all about. And now last, and this is McNemar. And as I told you, McNemar is like in within group. So we have already splitted file. It's I think 2 minutes. I will take more, nothing, not more than 2 minutes. And McNemar is within group. We use Friedman and repeated measure ANOVA within group, but quantitative variable. But McNemar, we have to use for qualitative nature of a categorical variable. Yes and no. Minor, moderate, severe. Okay, present and absent. But at 3 months baseline, we give treatment. There is a pain, and we give treatment. And after that, we want to see pain. How many patients have pain after treatment? There is a significant of treatment or not? Okay, so we want to see. There is a change in, okay, there is a change in patient. For example, at baseline, one patient saying, oh, I have pain. After that, injection is giving. And after like 3 months or 15 days, whatever, again check pain. So this patient say, okay, I don't have pain. It means treatment is like effective. So how many patients like say this? So we have to click analyze. Then we have to use this descriptive. As I told you, where is cross tab, like McNemar test in a cross tab. Analyze, descriptive and cross tab. Click here. And now you have to see, because we have already split file. This is a cross tab file, cross tab like tab or window. You can see dialog box. We have already splitted file according to group code. So there is no need of this. If we perform this, so suppose if we perform this according to the group code, we have already splitted file. So what happened? You can see here. No, there is no group code is in for split file. So it may not be useful in cross, because we have already splitted. And we don't need this. What we need, click analyze, descriptive, and then again cross tab, then remove these all. I want functional and vision problems. Baseline to, yeah, this is vision problem. This is functional problem. This is a baseline. So please put these two. These are in 0 and 1 and 2 format. Vision problem is yes and no, and functional problem is no, mild or moderate. Okay. So I have to click here, and please baseline or before and previous one, you have to bring in a row, and afterward like follow up, you have to bring in a column. So please click here and shift and arrow, select both, and then bring this, click here, will come here. Very good. But I want to show one by one. Okay, so like bring back to it. And where is a 3-month follow-up vision problem? Where is 3-month follow vision problem? Where is 3-month follow-up? Oh, this is 3-month follow vision problem. Yes and no format. Click here and then click in column. If there is a like 3 month and 6 months follow-up, and we want to like see 3 month and 6 months, then please put 3 month in row and column in 6 months. Then you have to click exact. There is no need to click exact now. There is no useful of this, because we have to use, but okay, it goes, no problem. But we have to use within group. So please click statistics, this cross tab in. There is no useful of chi-square also. But please like, okay, checked it, no problem. Then I have to click McNemar here and then click continue. Then click OK. And what I see, oh, well, now it's a treatment. And you can see here, There is a change of the subject from baseline to. At baseline, the vision problem is one any problem. Okay. And here 49 patients had vision problem at baseline. And what about what happened at 3 months? This is a problem. Okay. Yes. 27. Oh, there is a significant difference here. You can see 49, 49, and then 27. There is a significant difference here. You want to see, you want to get like percentage 49 by 57. 49 by 57, 86. Again, you have to get percentage 27 by 57. So this will not come 100, it will come other. 27 by 57, this means percentage. It means it is like less than 86. It is significant or not? We cannot use Fisher exact or chi-square test in this situation. We have to use McNemar. You can see here, Pearson chi-square is not coming significant. Fisher exact test also not coming significant because we have to take, there are two cells. So we have to take a Fisher exact test. It's not coming significant. But we have to take McNemar test for this. This is coming significant. Very good. But due to we don't know and we are using this Fisher exact test because there are two cells, we are using this. And this is not significant and this is actual this is significant and we are taking this, we are giving our result in journal, we are committing type 2 error. Type 2 error is accept null hypothesis when it falls. This is also serious problem. Type 2, type 1 error, reject the null hypothesis when it's true. Reject the null hypothesis when it's true. We have done in like Fisher exact test or chi-square when we took. Type 2 error, accept the null hypothesis. If we take this p-value, it means there is no significant association. There is no significant improvement in a 3-month baseline to 3 month in treatment group. So we are accepting null hypothesis. But actual, it is wrong. It is false. So we are accepting null hypothesis when it's like wrong, when it's false, it's called a type 2 error. Now again see, in control group, I want to see control group, no problem, very good. Here you can see at baseline, problem is in 47 and a 3-month problem is 49. Oh, 2 patients increase. Their total 58. So 47 divided by 58 around 81%. 49 divided by 58 around 81%, something like that. 2% increase. So I think 2 patients is not coming significant. You can see here, this is a McNemar test. Although by chance, if you take like this Fisher exact and this one, so it goes because also McNemar test is not significant. If you like take this Fisher exact test because one cell here is like here, so you have to take Fisher exact test 0.350 and you show like your result is non-significant, but also McNemar is non-significant. It goes, no problem. Now McNemar-Bowker test, last one, McNemar-Bowker test. And I told you that if there are group is more than two, then you will get automatically McNemar-Bowker test. There is no need to click here and there. Just click on McNemar. We have already clicked. So just follow these steps. And what I choose, descriptive statistic. Oh, 1 minute, sorry. Descriptive statistics, then cross step, and then vision. I have to remove this vision, click this, and I have to click this functional on base because I told you previous one must be entered in row. So you can interpret easily. You can take whatever you can take in like this one in row and this one in column, but you have to interpret. You have to know how to interpret something. There is no need not like mandatory you have to enter in row and column, but mandatory is how to interpret your result. That is must. Where is 3-month functional? Yeah, this one 3-month function. We have already exact statistics. We have already McNemar and chi-square. And then cells, we have already column. You can tick row. There is no problem. Okay, I've tick row on. Very good. Then click continue. And then you can see here. Whatever you want to tick, you can tick. This is triple. 0, 1, 2. 0, no problem, mild and moderate. 0, mild and moderate problem in functional vision. Also here, 0, 1, 2. Then I want to see what is the p-value. You can see here there is a mild problem. In baseline there is a 24 patients, but at 3 months there is a 17 patient. There is a shifting of the patient improvement. We have to see in moderate or severe there are 11 patients in baseline, but at 3 months only 3 patients. Oh, very good. There is improvement in treatment. So I want to see which p-value. You have to see p-value. This is McNemar. Again, if you are taking this 4 cells here, you can see here 4 cells. If you are taking Fisher exact test p-value, again, so what you will conduct type 2 error, because it's coming significant and you are not coming significant, and you will like lost a great opportunity of your treatment, your hard work, making this type 2 errors. Okay, then again we can see here in control, again 0, 1, 2 and 0, 1, 2. Yeah, again you can same 29 patient, either here 24 patient, here in moderate or severe in baseline you can see 6 patient, or here 11 patient. So it's increasing. Oh, okay, it's increasing. Or maybe its p-value is coming significant, but in worst phenomena. We have to see. Oh, very good. Okay, it's not coming significant. But in Pearson chi-square, if you are taking, there are 4 cells and you are taking Fisher exact test, this is coming significant. And actually it is not coming significant. So what you make? Type 1 error or type 2 error, you have to think. I will not say anything. Okay. So this is about your today's presentation. And now you can ask me questions, no problem.
Thank you, sir. Thank you for such a wonderful session.
Okay,
I hope our participants also have the same viewpoint on this.
Yeah.
So before closing the session, there are few queries which I want to put in front of you.
Yes, ma'am.
The first question is, what is the significance or what is the importance of knowing the degree of freedom? Why it is important to know the degree of freedom?
I have 7 years of experience in data analysis, and till now there is no significance of degree of freedom. When you are doing by hand calculation in your like MSc and in PhD and something BSc, and you have to do manually calculate all these things. Whatever test you have to do manually. Then you have to compare with the tabulated value. Then you need a degree of freedom. Otherwise, there is no need of degree of freedom here.
Okay, sir. The next query is how to check the normalcy of the data.
Oh yeah, I have already explained. No, I have already explained.
Okay.
Yeah.
The third one is, what is the difference between asymptotic significance and exact significance?
Oh, exact is exact. There is a correction, exact correction. Fisher is a statistician who did some corrections for if there is an error. So he he made some corrections. So exact p-value is exact value. Okay. And asymptotic is like you can see that like in bell shape, there are 2 tails. Okay. So these are called asymptotic. Okay. 2-tailed, asymptotic 2-tailed. Okay, ma'am.
Okay, sir. Sir, I think we are already extended the session. So
okay, thank you, ma'am.
From my side, I think we should close the session.
Okay, thank you, ma'am. Thank you.
Thank you, sir, for such a wonderful session. Thank you,
ma'am. Thank you.